Okay, welcome back. So, in the last class we started on a beautiful subject of which goes under kinetics of phase transition, and but it is essentially a thermodynamic treatment, and we have included this in this course because of the generality. In fact, phase transition itself, if you have noticed, is quite general. It does not talk of any given system, it is applicable to all systems. That means I am talking of nucleation, not just of gas liquid. At the same breath I am talking of freezing, formation of ice nuclei, melting, formation of water inside ice. I am talking of magnetic transition, in the presence of a magnetic field when it is first order, in the absence of magnetic field it is second order. Why the grand generality appeals to some people, this grand generality at the same time makes many people uncomfortable, because people many times like to think in terms of specific systems, specific examples. But there are things where generality is extremely helpful and useful, because you learn one thing you can apply to all different systems. As I was telling my ex-student in Japan, he learned these things in a class, this nucleation and spinel decomposition. He found it, he is an experimental physical chemist, not my own student, but he was just taking the course, and he found it extremely helpful. Even now he is so grateful whenever he comes. He is a professor now in IIT Madras or IIT Chennai. Whenever he comes to Bangalore, he makes sure that he comes and sees me. Such is the reach of such a problem that you can apply to almost many disciplines. Okay. So now we are trying to get this thing going. So basic idea then is that we have this kind of a scenario, and this is delta G R, and this is R, and this is the critical nucleus, and we have to cross this barrier. I described the analogy with chemical kinetics, where it is we know how to do it. Here we know partly because we know the probability of being in the top has to be Boltzmann, e to the power minus delta G star, that we know, but we do not know how to calculate the rate of going over. In chemical kinetics is a bond breaking and or twisting. There we can write the detailed motion of that molecule rotating or bond breaking, but here we do not have that. So how do we get it? This was the one which was done by Zeldo, which, as I told you, is a nuclear physicist. So the way it is now done is there are two factors, is the probability or number of critical, if you consider rate as a flow like water going through a pipe, the rate of water, we talk about rate of water flow. Similarly, a new phase is forming, and from the old phase, and if we can see that the rate as a time independent process, then then how do I so I will say, okay, number of nucleus at the top, a critical nucleus, number of critical nuclei NC, and that is I can find on the top of the barrier, and then at the rate it will go over. So this I said is the same thing that we do in chemical kinetics, this part, and this part is the one that is non trivial, and I need to calculate that. So if I now have a nucleus sitting here at the top, then what would let it, if I am sitting on the top, a nucleus sitting in the top, what will make it go over? It will make it go over if another particle comes and impinges on that. So I need a factor, so another more particles, actually not one, several, but this is the radius r. So this is already a pretty macroscopic coordinate. So by changing small r means several monomers is coming. So these monomers are going to impinge on this. They are very interesting thing, in many examples, many problems, we get this quantity. I remember I passed a comprehensive at in Brown University, because I could argue this one. This was the problem given in a comprehensive exam, in PhD exam, without telling us, and we didn't, that time I didn't know of nucleation, and but I could figure it out by using kinetic theory of gases, that okay, the number of molecules that can pass. I realized that what could be. Then I said, okay, we all done in Maxwell-Boltzmann kinetic theory of gases that there is a unit area of a surface, and the pressure is nothing but the molecules coming and colliding with it. What are the number of molecules colliding with it? That is within certain parallel pipe. Remember, we draw the parallel pipe, and okay, these are the number of molecules in this, and which has the velocity towards the wall. So the rate of impingement of monomers is very similar logic, and on the surface, but then also the surface area of the nucleus. Larger the surface area, more. Now you may argue why I am taking different surface area, because in different temperature the size of the critical nucleus is different. Remember, R star is 2 gamma by delta GV, and delta GV is temperature dependence. So as temperature becomes larger and larger, and I'll come to this little bit more detail now, or maybe I should just do now and then come back, because this is a very important thing. I had it in my last, I maybe forgot it. So if I now plot this delta GR against R at different temperature, then I know gamma is also temperature dependent surface tension, but much weaker than this thing. Delta GVR, however, when they are at equilibrium, two phases old and new, then this is 0, delta GV is 0, so R star is infinity. So when I go little bit below, then R star they start decreasing, but still can be very large. So I can consider the following situation, that I can say, okay, this is when it is large, very close to coexistence, then it so as I lower the temperature, so if it is T3, T2, T1, then T1 is greater than T2, greater than T3. So barrier comes down, size becomes small as delta GV increases. So this is the reason why the surface area depends very strongly on temperature, then also depends from system to system, because these temperature dependence and the free energy landscape completely varies. Like if I talking of melting, it's different from that of freezing, or more than that, more from gas liquid condensation. That's what I wanted to tell. So this nucleus with the surface S and C sitting. So then the rate would be proportional to the rate of impingement, let me call it beta I, and S and C. Okay. So this should be proportional to that, and then I need a rate to go over that, I call this Z. Then I can go now and write my so this is the expression then. So this is the rate probability of having a number of critical size nuclei, that is NC. Then this is the rate of impingement on the surface, and then the probability, there is also a probability that during the unit time this beta is the rate of impingement per unit time it can also disappear, that means it can also come down here. So there is a non-equilibrium process, and this is what brings it very close to chemical kinetics, that I will discuss a little bit later. That effect that it can come down is included through this factor Z, which is called the Zeldovich factor. Now we will go through the calculation, and the calculation is a little complicated, and but we have to live with it. This is one of the probably after our canonical ensemble calculation, this is the most detailed calculation that we will be doing, but we have to do that anyway, and we will go through that with the heroism. it is so this is the thing we have to calculate z. How do I calculate z? The way I calculate z now is that I consider as if a train is moving. So, the growth of cluster is going like this can also. So, I add 1, it goes there, then I add 1 more, a n minus 1 is becoming a, then a n plus n plus. It of course disappears, that I will consider later. Right now I am trying to set up a train, and my aim is that just as you are in front of a, if you have stood in front of a passing train, then this compartment after compartment going in front of you. When the train moves in a steady state velocity, then what happens? Each compartment comes to you at a regular interval, okay, and that is a steady state. Steady state means just the flow of water in a steady state, that means it is a time independent process. So, I want to find a time independent rate. Rate is always, when rate is a constant, is a time independent, it gives a steady flow. Complete time independence is equilibrium, when nothing is happening, okay, that is a if I take a derivative of all the quantities, then at equilibrium, then they are all 0, concentration time derivative of concentration is 0, but here it is not. This is the next time independent thing, that is steady state, but it is not equilibrium. So, we have to make a distinction between equilibrium time independent process and steady state time independent process. So, I am going to do here that steady state, because I want to study the rate. Whenever I talk of a rate, it is a time independent, it is a steady state, otherwise you do not have a rate. Then we say time dependent rate, that is a different thing altogether. Okay. So, now I am going to calculate the flow as if a train. So, however, this quantity that I call CNC, that this going over, I can write as Boltzmann, this is equilibrium, Cn is an equilibrium concentration. I now change my notation, I might change my notation from R dependence to N dependence. That means, because I want to talk of adding of impingement of particles on these things, and then growth I want to do in terms of number plane, the number of particles in the system. Then I know there is a 1-to-1 correspondence between radius, and if I assume a sphere, then volume into 4 pi by 3 r cube, if is 4 pi by 3 r cube is n number of particles, and then volume V. Okay. So, that means r scales as n to the power 1/3, because this volume of a one molecule, volume occupied by one molecule into number of molecules in the cluster NV, that has to be 4 pi by 3 r cube, both have same dimension as volume. Okay. This is a trivial. If that is so, then I know this is 4 pi by 3 r cube in per unit volume, then that is nothing but proportional to n, and that one volume I absorb in n. So, that because per volume and that V I multiply, so these become dimensionless, is just per dimension of energy per particle. And now there is a surface term which is r to the power r square is nothing but n to the power 2 by 3. Okay. So, my earlier expression minus 4 pi by 3 r cube plus 4 pi r square gamma, that becomes minus n delta G n plus gamma n to the power 2/3. Why I am going to n representation? Because I want to add a molecular picture. R does not allow me a molecular picture, it allows a thermodynamic picture, because I could do the surface tension, but now I add a molecular picture because I am adding molecules one by one and it is flowing. And then I have the following ingredients, I have the Boltzmann distribution, and I have conversion of delta G gamma to the power n to the power 3. Okay. Now, I want to see that how now I introduce a very important quantity, that is FNT. FNT is time dependent. This is the probability of having a particle, a cluster, a nucleus of n particles at a time t. Okay. Now, that thing is changing it is changing because I have a flow, and as a result of flow that this guy is decaying by, I am just saying the one way flow now. If I do the equilibrium, I would need both the two sides, that I will do later. So, this guy is changing because of that flow, the one way flow, very important, the one way flow, this is decreasing because molecules are moving out. So, then Jn minus Jn minus, that is the way this is changing. Jnt I already wrote, that is my impingement, verb time dependent probability, surface, minus, now this is very interesting. Now, this is n plus 1 becoming n also, and that is, so this is this Jnt, it is going to n to n plus 1, okay. So, it is going to n plus 1, but it is on the other hand n plus 1 becoming n, and n plus 1 becoming n by evaporating, that is n plus 1. So, if I consider this guy, then this guy is going on that, but in the previous step it is going to this, but on this enzyme a part of that is in the flow, it is going at that rate, but at the part of that is coming back. So, I am just considering this process, as I said I am going to consider only this process, and in this process it is going by impingement, but is also disappearing by evaporation. So, if amount going is some amount is coming back here. Now, I can do also this case, but doing one enough for to get me the flow. Okay. So, this is a positive forward and this is the backward. Of that I have an estimate of the rate of impingement on a surface from kinetic theory of gases, as I told you the Maxwell-Boltzmann. Fnt is the time dependent probability, a very difficult thing. Right now I will see that we do not need that, we need that if in a more difficult calculation. So, and I have the surface area of n and n particle. This is disappearing, the evaporation also depends on the surface area clearly, but how do I, so this I have a control, Sn I know, Sn plus 1 I know, surface, the surface of a sphere of radius r is n to the power 2/3, I know that. I do not know what is Wn plus 1. This is a very, very interesting condition here. How do I find Wn plus 1? Now, there comes a very, very important quantity. Let me get a page to explain that. So, Jnt beta I Sn and Fnt minus Wn plus 1 if n plus 1 t and Sn plus 1. Now, we use something, I go back, I have to calculate this quantity, and this is another beautiful thing that we use a lot in your chemical kinetics undergraduate reviews. We use the principle of detail balance, one of the most most respectable principle called principle of detail balance. Onsager used it, generalized it in microscopic reversibility, which in his famous 1932 paper, or irreversible thermodynamics, and he got Nobel Prize for that. Now, principle of detail balance says that if I have, now at equilibrium I have to consider back and forth, steady state I got a flow, you have to make a distinction. So, I have principle of detail balance is a very strong statement. It says that if you are at equilibrium, then it is not enough to have a steady time independent, but each step must be individually balanced. That means this step, the number of particles going up towards B to A and must be same as A to B. So, individual steps, this is the principle of detail balance or microscopic reversibility, extremely important. That is the only condition that guarantees equilibrium. So, equilibrium means flux is 0, no flux, it's everything is balanced. But we are ultimately calculating a steady state, we are flying a flow. But see how we are using equilibrium at the same time. This is exactly done many branch, as I told you, if you enzyme catalysis kind of thing Michaelis Menten, then you are doing Lindemann famous chemical first order kinetics unimolecular dissociation reaction, everywhere this is used, but it was initially first done by Zeldovich. Okay. Now, maybe all of them have done independently, but it is the same thing. At least I am just mentioning 3 very famous theories, but probably 10 theories uses this kind of logic. That is why I like nucleation, because it brings so much beautiful things. So, okay, now Jn equal to 0. If I put Jn equal to 0, then what that is an equilibrium, but I have already defined that Cn is the equilibrium distribution. So, at equilibrium f and t becomes time independent, but at equilibrium f and t equilibrium is nothing but my Cn. So, now I put 0 equal to beta I Sn Cn minus Wn plus 1 Cn plus 1 Sn plus 1. So, what does it mean now? That means I get Wn plus 1. So, Wn plus 1, this quantity now become equal to beta I Sn, I take it on that side, and then Cn divided by Cn plus 1 Sn plus 1. So, this is my Wn plus 1. So, I have now, by using the Riedel-Malens, I got an expression for Wn plus 1. Let me write this down clearly, because I will need it. So, Wn now what I am going to do now? I am going to put this quantity into this equation now. Okay. So, I am going to this expression is going to be substituted in this one. Once I do that, what do I get? Sorry. Bear with me for a minute. Okay. So, I got this now. Now, I notice the following thing, Sn plus Sn plus get cancelled and I get beta I common. So, I take beta I Sn out, I also take Cn out common, then I get F n t by Cn minus Fn plus 1 T by Cn plus 1. So, I get for Jn this expression. Okay. Now, if you look at this expression, what do you see? You see a beautiful thing. You see that these quantity, this Fnt, and they are now, I can write it in the limit of large n, I can call it a time derivative. So, this thing can be written as, because this Fn plus 1 is minus, there will be minus beta I Sn Cn and ddn ddn so Jn this beautiful thing.